Collision theory. There are three collision theories, which are molecules of reactants must collide in order to form products. Molecules must possess a certain minimum kinetic energy, which is called activation energy, to initiate the chemical reaction. Products are formed only when effective collisions occur between molecules. Effective collisions require the colliding molecules must have a kinetic energy equal to or greater than the activation energy. When the kinetic energy equal to or greater than activation energy, effective collision occur. Collisions occur at the correct orientation. Activation energy. The activation energy is the minimum energy required to initiate a chemical reaction. For example, we have reactants. For example, two reactants react together. These two reactants must have activation energy to initiate the chemical reaction. These two reactants must have enough energy to initiate chemical reaction. The activation energy may be gained through collisions of the molecules. Both reactants must collide together for forming the activation energy. The energy is used to break the bond between reactant particles. These two reactants together, the bond will be break between them by the activation energy. That energy is used to break the bond in the reactants. Then these atoms will form new bonds in the product. Orientation of collisions. The correct orientation means that the collision of molecules occur at the correct angle that favors the formation of products. For example, two Hi molecules forming I2 molecule and H2 molecule. So this Hi, H on top and I at the bottom, these two molecules collides, and reaction occurs because this collision is effective collision because both are at the correct orientation or at the correct angle. But for this one hydrogen on top, one hydrogen at the bottom, these two molecules collide. Ineffective collision occur when these two molecules collide. These two molecules collide at wrong angle or wrong orientation. So this is what we call ineffective collision. If the molecule collides at wrong angle or at the wrong orientation, no reaction will occur, no product will be formed. Next example, this CO molecule collides with oxygen molecule, but it collides at the wrong orientation. This O collides with another oxygen atom in the oxygen molecule. This is ineffective collision, so no product will be formed, no reaction will occur. But if the carbon in CO collides with the oxygen atom in oxygen molecule, effective collision occurs, so the product will be formed. That's how important orientation of collision is. It will affect the correct orientation of collision will affect effective collision. Transition state theory. The theory explains the activation energy as the energy required. This is the activation energy required by the reactant to form the activated complex or transition state at the transition state. So this energy required for the reactant to form activated complex. Activated complex is a temporary species formed by the reactant molecules as a result of the collision before they form the product. The transition theory is best explained by using the energy profile diagram. this is energy profile diagram. So this is the activation energy, the amount of energy required for the reactant to form activated complex or transition state. Transition state theory. This chemical process, CH3I reacts with OH minus to form CH3OH plus I minus. So from CH3I to react with OH minus before forming the product, after these two reactant reacts, but before forming the product, it will form activated complex. Means the I is about to break, the bond of C and I is about to break, and the bond of O from OH with C is about to form. This is what we call activated complex. It's after the reaction happen, after the reactant reacts, but before the product form. This is activated complex. Activation energy is needed to stretch and deform bond in order to reach transition state. This activated complex, we call it transition state. It's before forming the product, but after the two reactants react. So this is the energy profile diagram. We have the potential energy on the y-axis and reaction progress on the x-axis. The reactant CH3I reacts with OH minus. The molecule bends. Ci bond begins to break. So this C and I, the Ci bond begins to break, and the OH bonds is about to form. So this is activated complex or transition state. The activation energy, this is the activation energy. It's from the energy of reactant until the energy of the activated complex. That is activation energy. From energy reactant to the energy of activated complex, that is activation energy. This is the amount of energy required for reactant to form activated complex. That is activation energy. And then we also have activation energy reverse. Activation energy reverse is the energy required for the products to form the activated complex, form back the activated complex. This is the animation of transition state theory. These two reactants is about to form bond here at the activated complex or transition state, and then when it form products, the initial bond will detach. Energy profile diagram. We have different energy profile diagram for exothermic reaction, the heat release, and endothermic reaction, the heat is absorbed. So for exothermic reaction, initially the potential energy of the reactant is higher than the product. That's the difference with endothermic. For exothermic, reactant potential energy higher than the potential energy of the product. And for endothermic reaction, reactant potential energy is less than the potential energy of the product. So activation energy, energy required for the reactant to form activated complex. So here is activation energy, and again activation energy, energy required for the reactant to form activated complex. So this is the activation energy. And the delta H is negative, heat is released from reactant, to become product. This is the delta H from reactant to become product. Heat is released, and here delta H is positive, heat is absorbed from reactant, here from reactant to becomes the product. That is the amount of delta H. Example, a key reaction in the upper atmosphere is O3 plus O. The product is 2O2. The activation energy forward, the reactants to become the activated complex, that is activation energy forward, is 19 kilojoule, and delta H for the reaction is negative 392 kilojoule. So we know that this is exothermic reaction. Exothermic reaction, you have to draw the energy diagram. For exothermic energy diagram, the energy of reactant is higher than the energy of product. That is exothermic reaction energy diagram. So draw a reaction energy diagram and calculate the activation energy reverse given activation energy forward. Activation energy forward is the energy required by reactant to form activated complex or transition state. But the activation energy reverse is the energy required by the product molecules to form the activated complex. So this is the exothermic energy diagram. Exothermic reactant must be higher than the product because this is negative delta H here, negative delta H. So the reactant must be higher than the product, the reactant energy. So here, given the activation energy forward, reactant to becomes activated complex 19 kilojoule, and then the delta H for the reactant to becomes the product, it is negative 392. You have to write down all information given in the questions in the diagram, and then this is the activation energy reverse for the product to become back the activated complex. So when you need to calculate this from the product to become activated complex, you have here the delta H from product to the reactant, and then from reactant to activated complex you also have activation energy. So just total up 392 plus 19. 392 plus 19, not negative 392 plus 19. This negative is just showing that is exothermic reaction. It's just showing that this is exothermic reaction. So for activation energy reverse, you must plus 392 plus 19, not negative 392 plus 19. That's how you solve this activation energy reverse question.